If you want to process, preserve, and determine the stability of a food, then a food scientist or engineer would ask first, what is the water activity of food? We could explain it through a metaphoric diagram. Water activity indicates the energy state of water, that is, strongly bound water, weakly bound, and free water. Free water is in a high energy state, therefore can be used for physical and chemical changes and microbial growth. Strongly bound water contains a low energy state, that is relatively low mobile and most inert. Thus, chemical reactions and microorganisms are unable to use this water. Multilayer adsorbed water contains medium energy state, thus medium reactive. Free water is highly mobile, thus highly reactive. Another type of water exists in porous matrix. It is capillary water and refers to the water held in the narrow pores, spaces, and crevices of a matrix through surface tension, cohesion, and adhesion. It works against gravity and it is directly related to water activity through capillary pressure, which dictates how tightly the water is held. Smaller micropores show stronger capillary forces, thus a stronger holding capacity. In this video, I am explaining how the different energy states of water are linked to the water activity of foods. Please watch this video until the end and share the link if you like this video. This will support our channel to grow. We can relate the energy state of water to food products. In this image, we could understand that increasing water in foods increases the energy state of water. Therefore, the energy state of water in moist foods has a higher energy state compared to dry foods, since moist foods have more free or reactive water. Water activity originates from the chemical potential, fugacity, and thermodynamic equilibrium. Chemical potential describes the energy status of water in a system and determines how it can react or migrate or flow. The energy state was based on the chemical potential as introduced by Josiah Willard Gibbs in 1876. The chemical potential of a food is difficult to measure, and therefore air around a food system needs to be related to the chemical potential of a food. We could measure the properties of air above the airspace over water, jar A, and airspace above protein powder, jar B. One condition we need to comply with: air needs to be in equilibrium with the solid or liquid phase so that air property represents the solid or liquid characteristics. Chemical potential of a pure ideal gas increases logarithmically with pressure at a constant temperature. Mu equal to mu naught plus RT ln P by Ps, where mu is the standard chemical potential at reference pressure Ps, usually 1 atmosphere. R is the universal gas constant, 8.314 joules per mole per degree K. T is the absolute temperature in Kelvin, and P is the pressure of the ideal gas in Pascal. In the case of non-ideal real gas, fugacity represents an effective pressure. Fugacity represents the escaping tendency of a substance from a phase. In 1901, Gilbert Lewis first introduced the concept of fugacity. In this case, chemical potential is written as mu equal to mu naught plus RT ln F by Fs, where F is the fugacity at a given state and Fs is the fugacity at standard state. Because fugacity cannot be directly measured for solid foods, therefore scientists approximate it by vapor pressure. Therefore, fugacity is practically identical to the vapor pressure of water escaping from a food. Then water activity is defined from vapor pressure as AW equal to PW divided by PW naught at constant temperature, which is equal to relative humidity. The vapor pressure of water in food can be measured. However, it is not simple and easy. Therefore, equilibrium relative humidity of air surrounding a food is commonly considered as the water activity. This provides advantage since defined humidity sensors of great variety are available commercially. Thermodynamically, water activity is the ratio of vapor pressure of water in food and vapor pressure of pure water at constant temperature. From where relative humidity was linked, in 1801, John Dalton introduced the concepts of vapor pressure and partial pressure, and he explained the concept of saturation depending on temperature and relative humidity. Now we can understand these concepts considering this example. We have two glass jars. One contains water, jar A, and another jar B contains a protein powder. At constant temperature and equilibrium conditions, there is no net transfer of water from the water phase or powder to the air. If we measure the vapor pressure on jar A and jar B, then the ratio would be the water activity of foods. Alternatively, if we measure the relative humidity of the air in jar B, then it would be water activity of the powder protein. Measurement of relative humidity is commonly used since vapor pressure measurement is difficult and has complexity. We could place a relative humidity measuring sensor on the air phase of the jar and measure the relative humidity at equilibrium and constant temperature. This measured relative humidity is the water activity of the protein powder. Therefore, most of the commercial water activity meters use defined relative humidity sensors. These sensors have advantages and disadvantages, and I will explain these in another video. One important point needs to be considered that the moisture content of the sample in the jar must not be significantly changed, because water activity is directly related to the moisture content of the sample. We can solve this problem using a very low air space above the sample so that the equilibrium process does not increase or decrease moisture significantly in the sample. In addition, sample size should also be in such an amount that we can achieve equilibrium within a reasonably short time, as well as no significant change of the sample moisture. In addition, jar temperature should be maintained constant. We could observe that commercial water activity meters comply with these criteria and provide guidelines for their instrument. This concept of energy state of water leads us to consider different types of water with different degrees of binding energy in a food. Later, based on this basis, most well-known and widely used bed and gap moisture absorption isotherm models were developed. I will explain this in another video. I would like to thank you for watching this video until the end. If you like this video, then support us by sharing it to your links.